Hello and welcome everyone to today's lecture video, which is on the sine infinite product formula. So this is an infinite product that represents the sine function. Now, those of you that have done calculus and studied Taylor series are probably familiar with an expression of the sine function that involves an infinite sum. In fact, I have a video about that on this channel. This is an infinite product, more akin to what we were doing in our first video on the gamma function, where we express that as an infinite product. Now, this video should be accessible to anybody who's gone up to maybe junior year of high school. You don't need calculus for this content, so I'm hoping you'll all enjoy it. So just to briefly outline what we're doing today, it's very straightforward. In today's video, I'm going to exhibit the sine infinite product formula. I'm not going to go as far as to say that I'm proving it, because a proof of this formula actually does take some pretty advanced mathematics. We'll rigorously prove this formula when we cover some material and complex analysis. But it's enough to show a kind of reasonability argument for why this infinite product formula should equal the sine function, and that's what we're going to do today. So we're going to exhibit, not exactly prove, but exhibit the sine infinite product formula. So without further ado, here it is. This is really cool. The sine infinite product formula says that the sine of x, where x would be, let's say, an angle measured in radians, equals x times, so here we go, x times, open parentheses, 1 minus x squared over pi squared. Okay, let's close parentheses on that term, times, open parentheses again, 1 minus x squared over 4 pi squared. You can think of 4 pi squared as really 2 pi quantity squared, times 1 minus x squared over 9 pi squared. I hope you guys are seeing the pattern now. Close parentheses, next term, times 1 minus x squared over 16 pi squared, and so on. If you plug in x, the more terms you put into that product, the closer you get to the value for the sine function. So we're going to do one application from this amazing formula, which is a proof of the Wallis product. The Wallis product is a very famous formula for pi over 2, another beautiful pattern in math. The Wallis product says that pi over 2 is equal to the infinite product expression 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5 times 6 over 5. I hope you guys are seeing the pattern here now. Next term will be times 6 over 7. And so on. So that's where we'll end this video. But first we need to motivate the very concept of the sine infinite product formula. Where does that come from? So the motivating idea behind the infinite product for the sine function is this idea that every polynomial of the form, let's call it p of x, that's our polynomial p of x, where x is our variable, equals some constant a sub 0 plus the next constant, which we'll call a sub 1 times x to the first, plus the next constant a sub 2, times x squared, plus a sub 3 times x cubed, and so on, and so on. This is a finite polynomial, so it'll end with some constant a sub n times x to the n. If we take that polynomial and all of the coefficients are complex, and we set it equal to 0, then that polynomial can be factored into a product, not an infinite product, into a finite product with finitely many terms. And the product will look something like this. It'll be of this form. We can say p of x, which again equals 0 here, can be shown to be equal to the product c. C is just a constant, a leading constant outside of the expression, times x minus r1 times x minus r2. And what are these r's? These r's are the roots of the polynomial. Those are the values where when x is equal to r, 1, r2, etc., all up to, let's say, our last root, which we'll call r sub I, okay, x minus r sub I. When x equals any of these roots, when you plug it into the polynomial equals 0. And I will always be less than or equal to n. So if the polynomial has exactly n roots, then I will be equal to n. If there are any repeated roots, I will be less than n. And again, the r's are called the roots of the polynomial, the values at which the polynomial equals 0. The values for x, that is. So let's do a quick example to refresh how this works. Let's take the polynomial f of x, and let's make it a quintic polynomial, a degree 5 polynomial. So f of x can equal, let's say, x to the 5th minus 5x to the 3rd plus 4 times x. And we want to factor this thing. So the first thing to notice is that there's an x in every term of this polynomial, so we'll pull that out. We'll start by saying f of x equals x, but I'm going to write it as x minus 0 to really highlight that 0 is one of the roots of this polynomial. And that'll be times x plus 1, close parentheses, times x minus 1, close parentheses again, times x plus 2, close parentheses, times x minus 2. And if we look at these numbers, 0, 1, negative 1, positive 2, negative 2, well, those are just the roots of the polynomial. They're the zeros, or roots, of this particular polynomial that we've written out. Now, if we were to graph this function, f of x, this polynomial function, drop some coordinate axes down here. This is just a sketch, it's not perfect. But now we can graph also on the x-axis the zeros, the roots of the polynomial, negative 2, negative 1, 0, 1, and 2. And when we sketch the graph for this function, f of x, it looks something like this. Again, this is just a rough sketch, but it illustrates the concept that the roots of the polynomial are just those values for x where f of x equals 0. So this is, again, y equals f of x. That's the graph that we're drawing here. And those values, negative 2, negative 1, 0, 1, and 2, those are the roots of the polynomial, or the zeros of the polynomial. And the larger point here, the more general point, is that according to the fundamental theorem of algebra, what we did in this particular case can always be done with any polynomial, as long as it has complex coefficients, which is actually a very big set of numbers. That's the reals and the imaginary numbers together. Any polynomial can be factored in this way, as a product of the form x minus the first root times x minus the next root, and so on. So what does all this have to do with the sine function? Well, we know from our work on Taylor series, and if you're not familiar with this subject, see my earlier video on Taylor series. I derived this. We know from our work on Taylor series that the sine function can itself be written as an infinite polynomial of the form sine x equals x minus x to the third over 3 factorial. 3 factorial, of course, is 3 times 2 times 1, plus x to the fifth over 5 factorial, minus x to the seventh over 7 factorial, plus x to the ninth over 9 factorial, minus x to the 11th, I'm sure you all see the pattern by now, over 11 factorial, and so on. So here's a natural question which Euler posed. If we can write sine of x as a polynomial, can this infinite polynomial, it's a polynomial that never ends, right? But it's an infinite polynomial, could that somehow be factored? So if we're going to begin to think about how we would factor that infinite polynomial for sine of x, we should start by considering the graph of the function. So here's y equals sine of x. I'm going to drop down some coordinate axes here. So that's my y and my x-axes. I'll label them there, x and y. What does sine of x look like? Well, sine of 0 equals 0. So I really want to focus on the values for which sine of x equals 0. And we can see, based on our graph of the sine wave, that sine of x equals 0 on the positive x-axis whenever x equals pi, 2 pi, or 3 pi, and so on. And let's look at the negative x-axis. Sine of x equals 0 at negative pi, at negative 2 pi, at negative 3 pi, and so on again. So, to borrow from our terminology with polynomials, we'd say the function sine of x has infinitely many zeros. You can see that this function is hitting the x-axis infinitely many times. And in fact, sine of x has its zeros, equals 0, for all values where x equals plus or minus n times pi. In other words, whenever x is an integer multiple of pi, sine of x will equal 0. So while our goal is to derive an infinite product formula for sine of x, to do that, Leonhard Euler actually considered a closely related function to sine of x. Namely, he considered the function y equals sine of x over x. And this is sometimes called the dampened sine wave. And it's pretty straightforward to see why that is, because sine of x itself is bounded in magnitude between y equals 1 and y equals negative 1. If x is increasing without bound, then the entire wave will be dampened as x grows. Now, unlike the sine function, sine x over x approaches 1 as x goes to 0. It's undefined at 1, but the limit is equal to 1. And then it has all the same zeros otherwise that the sine function has. So sine x over x equals 0 at x equals pi, at x equals 2 pi, again at x equals 3 pi. So we can just sort of plot this out. And you can see that as x is getting bigger and bigger, the wave is being dampened. So that's what it looks like on the positive x-axis. And now we'll try to draw sine x over x on the negative x-axis. It's symmetrical across the y-axis. It's an even function. And again, it has all the same zeros on the negative x-axis, negative pi, negative 2 pi, negative 3 pi, all the same zeros as sine x, with the one exception of the value of x equals 0, where the function then equals 1, or becomes infinitely close to 1. So I'm just going to finish filling out that graph, labeling my axes. And now this function, sine x over x, also has a Taylor series expansion. And it's very straightforward to derive it. We see that sine x over x would just be equal to the Taylor series expansion for sine x, all divided by x. So in other words, it would equal to, open bracket, x minus, here's our Taylor series for the sine function, x cubed over 3 factorial, that's 3 times 2 times 1, plus x to the 5th over 5 factorial, that's 5 times 4 times 3 times 2 times 1, minus x to the 7th over 7 factorial, and so on, close brackets. That whole Taylor series expansion will be divided by x. And now when we do that, all we have to do is reduce each exponent by 1. So x over x equals 1, x cubed over x equals x squared. Then we get x to the 4th, x to the 6th, and so on. So our Taylor series for sine x over x is going to equal 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial and so on. So I'm just going to bring that Taylor series expansion up to the top of the screen above the graph there. And I just want to highlight again that all of these values, negative 5 pi, negative 4 pi, etc., positive pi, positive 2 pi, 3 pi, 4 pi, those are the same values for which sine x has zeros. The zeros of sine x over x are the same as the zeros of sine x, with the exception of the point of discontinuity at x equals 0. And again, at that point, we see clearly from the Taylor series that the limit as x approaches 0 for sine x over x equals 1. As we let x get infinitely close to 0, all of those terms in our Taylor series go to 0 except for that leading constant term, 1. And I'm emphasizing this here because we're going to make use of this fact in just a moment. So, if we were to try to factor sine x over x as an infinite product formula, how would we go about doing that? Well, again, we have our Taylor series for sine x over x, which is equal to 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. Right, this is our infinite polynomial representation for sine x over x. I'm just going to write out a couple more of these terms so we have a nice expanded series here. Okay, so minus x to the 10th over 11 factorial plus dot, dot, dot. That should be enough. So there's our infinite polynomial representation for sine x over x. And the natural question would be, how would we factor this infinite polynomial? Well, based on the example we did before, where we factored a finite polynomial, we can take a guess. We can factor this polynomial by its roots. What do I mean by that? Well, what I'm going to try to do is write sine x over x equals some constant, which is to be determined. We'll call that constant c. That's some constant there. Times x minus, let's call the first root pi, times x minus negative pi, or x plus pi, if you will. That's a double negative there. Times x minus 2 pi, close parenthesis, times x minus negative 2 pi, or plus 2 pi. We'll write that there. Close parenthesis, times x minus 3 pi, close parenthesis, times x plus 3 pi, and so on, right? Those integer multiples of pi are just the roots of our function sine x over x. So I'm just erasing that text here. And now we need to find c. Well, to do that, all we have to do is set x in this equation equal to 0. When we let x equal 0, we recall that the limit as x approaches 0 for sine x over x, the limit as x approaches 0 for sine x over x equals what? Equals 1. Okay. So if we set x equal to 0, then we get 1 equals c times 0 minus pi, close parenthesis, 0 times 0 plus pi, close parenthesis again, and so on for the rest of our product. We just plug in 0 for x there. And so we get 1 equals c times negative pi times positive pi is going to be negative, open parentheses, pi squared. Okay, so that's a negative term there, times negative 2 pi times positive 2 pi is negative 2 pi quantity squared. It's important to note that all of these terms in this product are negative, times negative 3 pi quantity squared times negative 4 pi quantity squared, and so on. So I'm going to bring this now to the top of the screen. And to solve for c, all I have to do is divide through. So when I do that, I get c equals 1 over this entire product written in yellow here. So c equals 1 over negative pi squared times negative 2 pi quantity squared times negative 3 pi quantity squared, and so on. Now, some of you might object that this isn't really an expression for a constant at all, right? We have an infinite product in the denominator there. But that's characteristic of these infinite product formulas. We're not just going to get a finite constant. It will depend on how many terms we evaluate this infinite product to. So what we end up getting here is sine x over x is going to equal x minus pi times x plus pi, parentheses, times x minus 2 pi times x plus 2 pi close parentheses again, times x minus 3 pi times x plus 3 pi. And this is all going to be multiplied by our constant c, which we just determined. C is 1 over negative pi squared. So I'm going to put that in the denominator. Times negative 2 pi squared. Times negative 3 pi quantity squared. And so on. So this is our expression for sine x over x when we've solved for c. Okay. So now moving that expression to the top of the screen here, I'm going to combine some terms. So I'm going to put brackets around these terms like so. Every two terms, we're going to FOIL them out, to borrow an expression from middle school algebra. We get sine x over x equals x squared minus pi squared, close parenthesis, times x squared minus 4 pi squared, close parenthesis again, times x squared minus 9 pi squared, and so on. And that's all over negative pi quantity squared times negative 2 pi quantity squared. So in other words, negative 4 pi squared times negative 3 pi quantity squared, which of course is negative 9 pi quantity squared, and so on. And now we can do some nice cancellations. That pi squared in the denominator will cancel the pi squared in the first term of the numerator, and that will become a plus 1 up there. And our x squared term will become minus x squared over pi squared. Similarly, in the next term, the minus 4 pi squared cancels, and in the numerator that becomes plus 1, and our x squared term becomes minus x squared over 4 pi squared. And so on. Here's the next one. That negative 9 pi squared will cancel in the numerator, and we'll get a plus 1 there, and the x squared term will become minus x squared over 9 pi squared. So when we clean this up a little bit, we get sine x over x equals 1 minus, positive 1 minus x squared over pi squared, close parenthesis, times, again, positive 1 minus x squared over 4 pi squared, times positive 1 minus x squared over 9 pi squared, times 1 minus x squared over, we'll do one more term, over 16 pi squared, and so on, dot, dot, dot. So now we're very close to being done, because all we have to do is multiply through by x to find that sine x equals x times 1 minus x squared over pi squared times, close parentheses, times 1 minus x squared over 4 pi squared, close parenthesis again, times 1 minus x squared over 9 pi squared, close parenthesis, times 1 minus x squared over 16 pi squared, and so on, dot, dot, dot. So I'm going to put a box around these two really beautiful formulas. These are our infinite product expressions for sine x and sine x over x. Now those expressions are so elegant that we should probably do a sanity check. So again, I'm not going to rigorously prove these expressions. That requires some powerful theorems that even Euler actually didn't have access to in his time when he came up with these infinite products. But we should think about convergence. Does this infinite product converge? Again, I'm not going to prove it, but I am going to show that it does meet one necessary condition for convergence. For an infinite product expression, and I'll write the general form for an infinite product expression, we use capital pi, and we'll write underneath that n equals 1, and on top infinity, and here's our term a sub n. So this is the infinite product as n goes from 1 to infinity of our product a sub n. So in other words, a sub 1 times a sub 2 times a sub 3, and so on. That's what that expression means. It's a necessary, though not in itself sufficient condition, that in order for this infinite product to converge, our general term a sub n has to go to a certain limit. It has to equal 1 in the limit as n goes to infinity. And this is very much analogous to infinite sums, where we need our general term to go to 0. If a sub n doesn't approach 1, then the infinite product will diverge. It'll diverge to infinity. So now let's look at our infinite product formula for sine of x, and we'll consider the general term in that infinite product. So we found sine of x equals x times the infinite product from n equals 1 to infinity of 1 minus x squared over n squared times pi squared. So let's look at this general term, 1 minus x squared over n squared times pi squared. For any fixed value of x, we fix any x in that expression, and we look at the limit as n goes to infinity. Our general term is going to be 1 minus x squared over n squared times pi squared. And we're letting n get bigger and bigger while we've fixed a specific x, and we don't really care what x equals. It's not changing. Then we see that that part of the expression goes to 0, and so the general term goes to 1. So we've met the necessary condition. We have reason to hope that it will converge. So let's turn this line of thinking now to another function, and I want to consider cosine of x. So let's draw our coordinate axes again. There's my y-axis. Sorry, it's a little bit on a slant, but this is just for illustrative purposes, and there's my x-axis. Now cosine of x, like the sine of x, reaches a maximum of positive 1 and a minimum of negative 1, but cosine of 0 equals positive 1. So we're drawing our cosine wave there in the positive direction and in the negative x direction. Just continuing the cosine function there. And where are the zeros? The zeros are at x equals pi over 2, x equals 3 pi over 2. And just continuing this a little further, we have another 0 at x equals positive 5 pi over 2. And then the negatives of those same values. So there's a 0 at negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on. That's our cosine graph. And again, these are going to show up in our derivation for an infinite product representation of the cosine function. These are the zeros of cosine of x. So let's note here, cosine of 0 equals 1. We're going to make use of that fact in just a moment. We want to write, just as we did before with our sine function, cosine of x equals some constant c, which we haven't yet determined, times x minus the first root, which we can call pi over 2, close parenthesis, times x minus the next root, which would be negative pi over 2, so that's a double negative, making it a plus pi over 2. X minus pi over 2 is the same thing as x plus pi over 2, times x minus 3 pi over 2, close parenthesis, times x plus 3 pi over 2, double negative again, and so on. Dot, dot, dot. Now again, we'll solve for c by setting x equal to 0. So when we do that, cosine of 0 equals 1. So cosine of 0 will equal c times 0 minus pi over 2 times 0 plus pi over 2 times 0 minus 3 pi over 2 times 0 plus 3 pi over 2, and so on. And so we find again that c equals 1 over something. This time it equals 1 over negative pi over 2 quantity squared, which would be the same thing as negative pi squared over 4, times negative 3 pi over 2 quantity squared, which is the same thing as negative 9 pi squared over 4, times the next term would be negative 25 pi squared over 4, etc. And that all equals c. So therefore, we can write for our product cosine of x equals what we have up here. This is going to multiply by c. And again, I'm going to combine terms together, two at a time. So when I do that, I have x minus pi over 2 times x plus pi over 2. That equals x squared minus pi squared over 4. And the next one would be x minus 3 pi over 2 times x plus 3 pi over 2. That would be x squared minus 9 pi squared over 4. And the one after that would be x squared minus 25 pi squared over 4, and so on. And the denominator that comes from c, that will be minus pi squared over 4 times negative 9 pi squared over 4 times negative 25 pi squared over 4, and so on, dot, dot, dot. So I'm going to move that last line to the top of the screen, and when we start doing cancellations, we see that when we divide by negative pi squared over 4, that negative pi squared over 4 in the numerator becomes positive 1, and the x squared term becomes minus 4x squared over pi squared. And then in the next term, when we divide out by negative 9 pi squared over 4, that negative 9 pi squared over 4 in the numerator also becomes a positive 1, and the x squared term there becomes negative 4x squared over 9 pi squared. Then when we divide out by negative 25 pi squared over 4, that term in the top becomes plus 1, and the x squared term becomes minus 4x squared over 25 pi squared. So we see that all of the terms in our denominator cancel, and we find this expression for cosine x equals 1 minus 4x squared over pi squared, close parentheses, times 1 minus 4x squared over 9 pi squared, close parentheses, times 1 minus 4x squared over 25 pi squared, close parenthesis, and so on. So we can put a box around this too. This is our infinite product expression for cosine of x. It's another beautiful formula, and we derived it the same way that we derived our infinite product expressions for sine x and sine x over x. So to review our work so far, we found sine x is equal to x times 1 minus x squared over pi squared, close parenthesis, times 1 minus x squared over 4 pi squared, close parenthesis again, times 1 minus x squared over 9 pi squared, close parenthesis, times dot, 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 and so on. And we found that cosine x also has a beautiful infinite product representation. It equals 1 minus 4x squared over pi squared times 1 minus 4x squared over 9 times pi squared times 1 minus 4x squared over 25 pi squared, close parenthesis, and so on, dot, dot, dot. And as lovely as these formulas are, unfortunately there's a problem with the way that we've derived them. So as I've mentioned already, these derivations are not rigorous proofs. The formulas are correct, you don't need to worry about that, but the way that I've derived them lacks the rigor that we would expect from a real mathematical proof. And the reason for that is that there's an infinite number of functions that have these exact same roots for sine x and cosine x. In other words, we have a problem involving uniqueness. How do I know that these infinite product formulas actually are the formulas for sine x and cosine x and not some other function that has the same roots? For example, e to the x times sine x has the exact same roots as sine of x. There's nothing in my derivation for the sine function that I've given here that can really distinguish between these two functions. So in other words, how do we know that these factorizations that we've derived are actually equal to our trigonometric functions? Again, they are, but how do we really prove it? Well, again, I can't prove it fully here, but I'm going to offer you what I think is a really persuasive plausibility argument. And for this argument, I'm going to ask you to recall the following fact from high school trigonometry class, which is that the sine of 2 times x, the sine of double any angle x, equals 2 times the sine of x times the cosine of x. This is just a double angle identity that is drilled into us in high school trigonometry class. Sine 2x equals 2 sine x times cosine x. And now we're going to make a slight rearrangement to this identity, namely that cosine of x then must equal sine of 2x over 2 times the sine of x. And now we're going to substitute in the identities that we found for sine of x. So that means that sine of x, as we saw before, equals this expression, x times 1 minus x squared over pi squared times 1 minus x squared over 4 pi squared, etc. And therefore sine 2 times of x, plugging in 2x into that formula, means that sine 2 times x equals 2x. We're plugging that in for x. Times 1 minus 2x quantity squared is 4x squared over pi squared, times 1 minus, again, 4x squared over now 4 pi squared, and so on. We're just plugging in 2x for each of these terms. So 1 minus 4x squared over 9 pi squared, close parenthesis, times 1 minus 4x squared over 16 pi squared times 1 minus 4x squared over 25 pi squared. Okay, so that's what we would have for sine 2x in our infinite product expansion. So what we're going to try to do is derive an infinite product formula for cosine of x, making use of this trigonometric identity that cosine of x equals sine of 2 times x all over 2 times sine of x. Now, we have from our infinite product formula for sine of x the following facts. Namely, sine of 2 times x would equal this expression which we just found. And 2 times sine of x will just equal 2 times the infinite product formula for sine x that we found earlier. So we can put these facts together and write sine of 2 times x over 2 times sine of x equals our infinite product expression for sine 2x divided by our infinite product expression for 2 times sine of x, which I've written here. So I'm going to move that expression to the top of the screen and make some simplifications here. So all of those expressions, 2x quantity squared, those become 4x squared. So I'll do that with all of them. This one here becomes 4x squared. And same goes for all of the next terms, so I'll just do them all at once. Those all become 4x squared. And we can make a further simplification in the numerator here where we have terms like 1 minus 4x squared over 4 pi squared. Those 4's cancel out. Nothing doing in the term right after that, but then we have 1 minus 4x squared over 16 pi squared. In fact, we have a factor of 4 in every other term, so the next one after we'd have 1 minus 4x squared over 36 pi squared. We can divide out of 4 there as well. So those terms where we've made cancellations become 1 minus x squared over pi squared, 1 minus x squared over 4 pi squared, and 1 minus x squared over 9 pi squared. So I'll just write that out here. So let's clean this up a little bit. Again, that will be x squared over pi squared. Skip the one with the 9 pi squared term, but then the one after that, that becomes x squared over 4 pi squared. Skip the one with the 25 pi squared term, but the one after that becomes x squared over 9 pi squared. And now I can make cancellations between the numerator and the denominator. So the 2x's cancel in the numerator and denominator. And then looking at the next term in the denominator, 1 minus x squared over pi squared, there's a matching term up there in the numerator. 1 minus x squared over 4 pi squared, there's a matching term up there in the numerator. 1 minus x squared over 9 pi squared has a matching term up there in the numerator. In fact, every single term in the denominator gets canceled by each alternating term in the numerator. So this is really cool. What are we left with? We're left with the expression cosine x equals 1 minus 4x squared over pi squared, close parenthesis, times 1 minus 4x squared over 9 pi squared, times 1 minus 4x squared over 25 pi squared, close parenthesis, and so on, dot, dot, dot. But this should look very familiar. In fact, this is the infinite product expansion for cosine of x that we found earlier. But now we've derived it from trigonometric identities rather than from reasoning about the roots of cosine x and making an argument analogous to the fundamental theorem of algebra. So it's really not a coincidence that these infinite product expressions, which we believe to equal the trigonometric functions, obey trigonometric identities. So again, we haven't rigorously proven that these infinite product expansions are indeed our trigonometric functions, but the fact that they obey trigonometric identities is a nice piece of evidence that they are. And I'm going to end this video with an application for our sine infinite product formula. As promised, we're going to prove the Wallis product. And for those of you who watched my video on the infinite product formula for the gamma function, we made use of the Wallis product in that video, and I said there, I don't really have time to prove it, but stay tuned. Well, here's the proof for the Wallis product formula. So the Wallis product says that pi over 2 equals 2 over 1 times 2 over 3 times 4 over 3. There it is. Times 4 over 5 times 6 over 5 times 6 over 7 times 8 over 7 times 8 over 9, and so on. And I'll put some parentheses around these pairs of terms. And let's put a box around it. This is the Wallis product for pi over 2, a really beautiful formula also. We'll put that there. And we're going to prove this by making use of our infinite product formulas. So we know that sine of x over x equals this infinite product, which we found already. So we're going to now let x equal pi over 2. And when we do that, we get sine of pi over 2 divided by pi over 2. Sine of pi over 2, of course, just equals 1. So this will be 1 over pi over 2. And then taking reciprocals, that equals 2 over pi. When we plug this into our sine x over x infinite product expansion, we get 2 over pi equals 1 minus pi over 2, quantity squared, over pi squared, close parenthesis, times 1 minus pi over 2, quantity squared, over 4 pi squared, close parenthesis, times 1 minus pi over 2, quantity squared, over 9 pi squared, times 1 pi over 2, quantity squared, over 16 pi squared, times 1 minus pi over 2, quantity squared, over 25 pi squared, close parenthesis, dot, 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 and so on. So now to simplify this expression, we're first going to note that pi over 2 quantity squared equals pi squared over 4. So I'm going to replace all of those pi over 2 quantity squareds with pi squared over 4. So let's just do them all at once. I'm going to just erase them and replace them all at once. So this one can go, and this one can go. Same with the rest of them. And they'll all be replaced by pi squared over 4. But now when I look at that first term, 1 minus pi squared over 4 over pi squared, that's the same thing as writing 1 minus pi squared over 4 pi squared. And the next term could be rewritten as 1 minus pi squared over 4 times 4 pi squared, or 1 minus pi squared over 16 pi squared. The next one would be rewritten 1 minus pi squared over 4 times 9, which is 36 pi squared. The one after that would be 1 minus pi squared over 64 pi squared, and then 1 minus pi squared, there should be a squared there, over 100 pi squared. And now, of course, all these pi squared terms can cancel. Again, that should be a pi squared, and it cancels the pi squared in the denominator there. And so when we do that simplification, we're left with the expression 2 over pi equals 1 minus 1 over 4, close parenthesis, times 1 minus 1 over 16, close parenthesis, times 1 minus 1 over 36, times 1 minus 1 over 64, times 1 minus 1 over 100. And now when we look at these terms, each of these terms is actually the difference of two squares. One is a perfect square, and each of those fractions is a perfect square. And so I'll make use of the algebraic identity a squared minus b squared, that's the difference of two squares, equals a plus b times a minus b. So I'm actually going to factor these terms out. So I get 2 over pi equals 1 minus 1/2. Remember, 1/2 squared is 1/4, so 1 minus 1/2 times 1 plus 1/2, close parentheses. And then we'll do the next one, that would be 1 minus 1/4 times 1 plus 1/4, close parenthesis, and so on. So we're almost done simplifying this. We have 2 over pi, then would equal 1 minus 1/2 is 1/2. 1 plus 1/2 is 3 over 2. So that's times 3 over 2. Close parenthesis. Times 1 minus 1/4, that would just be 3/4, 3 over 4. Close parenthesis again. Times 1 plus 1/4, that's 5 over 4, 5/4. Times 1 minus 1/6, that's 5 over 6. Times 1 plus 1/6, and I'm sure you guys can see where this is going, that equals 7 over 6. Times 1 minus 1/8, that's 7 over 8. Times 1 plus 1/8, that's 9 over 8. And so on, dot, dot, dot. And now all we have to do is take the reciprocals. So when we take the reciprocals of both sides of this equation, we get pi over 2 equals 2 over 1 times 2 over 3. How cool is this? Times 4 over 3 times 4 over 5 times 6 over 5 times 6 over 7 times 8 over 7 times 8 over 9, and so on, dot, dot, dot. And I'll put parentheses around pairs of these again just to make it look more like what I have boxed on top. That's the Wallis product, which we've derived from our infinite product expansion for sine x over x. Well, that's it for today. Thanks for watching, and if you enjoyed this video, please click like and subscribe to my YouTube channel. See you next time.